Welcome to lesson 18 of the Advent of SysML v2. This is a training series consisting of short videos and exercises brought to you by Sensmetry in collaboration with Vince Molnár. My name is Kęstutis, and yesterday we explored actions together, defining what systems do step by step. But not all behavior follows a script. In this lesson, we are learning state machines, how to model systems that react to events. By the end of it, you'll know how to model states and state transitions, how to handle nested states and parallel states, how to define entry, exit, and do actions. Many systems operate by continuously reacting to events in their environment. The behavior of such systems is challenging to describe with a workflow-like action models. This is because a significant part of their operation involves waiting for events and then reacting, potentially in an infinite loop. The reaction is determined by two things: the event that occurred and the system's history, encoded in its state. A state captures the information a system must remember to decide how to react. In engineering, we separate data variables from the control location of our logic and call only the latter a state. For example, a system can be on and off. These influence how it reacts to different stimuli. Transitions happen when a system moves from one state to another in response to an event. Transitions usually also prescribe an action to perform as the system's reaction. Together, states and transitions form a state machine. Events are usually one of three things: changes in the value of something, timers expiring, or the reception of messages from other entities. We will illustrate all three today. As we saw in lesson 13, item models entities exchanged between systems. We start by defining items for the events our state machine will send and receive. Lines 4 through 7 show simple event items: start mission, end mission, approach, and next. They are empty because the type name alone carries the meaning. Lines 9 through 14 show items with attributes. Command has a string for the command text, and status has a string for status messages. Here are two patterns. Empty items are easier but create many definitions. Parameterized items are fewer but require more complex patterns. Now let's build our state machine, the reindeer controller. This represents Santa's sleigh logic for controlling the reindeer on Christmas Eve. Line 16 declares a state definition using statedef keywords. Just like partdef defines structure, actiondef defines behavior, statedef defines the state machine blueprint. State machines rarely stand alone. They need to access data and communicate. Lines 17 through 19 define three attributes the state machine monitors. Lines 20 and 21 define two ports for communication using refport keywords, references to ports owned elsewhere. Lines 22 and 23 establish the initial state. Note keywords entry then. When this state machine activates, immediately go to idle state. Lines 24 declares the idle state, a state usage. These rarely need definitions unless they are complex enough to reuse. Lines 25 through 28 show a complete transition in shorthand notation. Let's break it down. The source is the lexically previous state, idle, just like in shorthand succession in lesson 17. The trigger on line 25 accepts start mission via HMI. State machine waits for this item via this port. The guard on line 26. The transition only fires if there are 9 reindeer with at least 36 kilowatts of power. The effect on line 27 send command to the reindeer. The target on line 28 then go to state mission. So when does the transition execute? Three conditions: the source must be active, the trigger is satisfied, and the guard is true. When all three are met, the effect executes, source deactivates, and the target activates. A composite state is a state with nested substates. In SysML v2, there is no difference between composite and basic states. Both use state usages. When a composite state is active, one or all of its substates must also be active. What does it mean, one or all? The parallel keyword decides. In parallel states, all substates are active simultaneously and there can be no transitions between them. Line 29 declares mission composite parallel state. When it is active, both monitoring reindeer and controlling reindeer substates are active at the same time. This captures that these aspects are orthogonal, they operate independently. The monitoring state logic tracks energy transitioning between nominal and low energy states. Controlling state logic manages flight phases, taking off, flying, landing, and waiting. We can perform actions when transitions occur, but we can also link actions directly to states. Entry actions execute when state becomes active before anything else. Exit actions execute when leaving a state as the last thing. Do actions start after entry and continue while the state is active. They can be interrupted if state is left early. Lines 34 through 38 show the low energy state with all three options. On entry, send the low energy status alert. While in the state, continuously perform action blink LED. Assume it contains a loop. On exit, send a recharge status message. This is the complete life cycle. Entry sets things up, do performs ongoing work, exit cleans things up. Next, let's explore the longhand transition notation and other types of triggers. Lines 40 through 47 show named transitions using the longhand notation with transition keyword. The keyword first specifies the source explicitly. These are useful when you need to name transitions or when multiple transitions share a source. Lines 42 and 46 show the change triggers, except when average energy less than 50. These transitions fire automatically when the Boolean expression becomes true, perfect for monitoring thresholds. Lines 53 and 60 show relative time triggers with except after keywords. These fire after a duration has elapsed since entering the state, like waiting 60 seconds after takeoff before transitioning to flying. SysML v2 also supports absolute time triggers using except and keywords. This is not shown here, but useful for scheduled events like launching exactly at midnight. So the four trigger types, reception of items, change events, relative and absolute time, cover most reactive scenarios. If you find yourself struggling with action models trying to control when actions execute, remember, state machines might be a better choice. You have now learned the fundamentals of state-based behavior modeling in SysML v2. To practice these skills, we challenge you to develop Santoslay's cruise control state machine model. Check the blog post for detailed instructions. Share your experiences and feel free to ask questions in our community forum. Links and information on how to access Syside cloud platform are in the video description. Like the video, subscribe to our YouTube channel, and click on the bell icon to get notified about future lessons. Take care and happy modeling!